I want to show you a derivation for the ideal gas law. We're going to start with a particle in a cubical box of side length L, so all three side lengths are L. And this particle is going to travel in the x direction, bounce off the wall, turn around and travel in the opposite of the x direction, or minus x direction, bounce off the wall, and come back to where it is. So the path length for the particle is going to be 2L. Path length is equal to 2L. Now, we ought to talk about what the velocity of the particle is going to be. Velocity, as you know, is distance per unit time. Distance per time, which in our case is going to be 2L over whatever the change in time is, delta t. We'll call that Vx, the x direction. Now, we can take the component of the particle that's traveling in the x direction as opposed to having all of the particle travel in x. And we could also talk about the component in the y and z directions. And then we would have Vx plus Vy plus Vz is equal to the total velocity. And then if we substitute in 2L over t, we'd have three of those, Vx, Vy, and Vz, times 2L over delta t, which would give us 6L over delta t is equal to the general total velocity. And then also, and of most importance to me, is that delta t would be equal to 6L over nu. This is the piece I want to use, and this is the reason that we went through this little bit. All right, let's get another color here, and we will talk about momentum. Let's see, there's a color I like. And we will talk for a second about momentum. All right. There we go. All right, so we have the momentum. We'll call momentum P. That's traditional. Momentum in the forward direction. And again, we'll stick with the particle, just the x component of the velocity for the moment. And we'll say that the momentum is Vx, or m mass times velocity. And then in the reverse direction, it's obviously going to be going the other way, so it's going to be the negative of mass times velocity. And if we wanted to look at the change in momentum, that would be mass times velocity in the x direction minus negative mass times velocity in the x direction. And that would be 2 times a mass times a velocity in the x direction. I can generalize this, and if I do, I will get delta P simply equal to 2 times the mass times the velocity. Okay, and we'll move on to force. I'll give it yet a slightly different flavor for the color here, but we'll move on into force. Force is a change in momentum over the change in time. That's Newton's equation, and you also see it written as ma. But if you looked it up, momentum being mv and a being dv dt, this becomes the change in momentum over the change in time. So we can write this down then as the change in momentum, which we've developed right there, is 2 mass times velocity. And the change in time, which we've developed right here in blue, is 6L over nu, or nu over velocity. And so that becomes 2mv squared over 6L, which is equal to mv squared over 3L, which is our force. All right, let's cycle back through here, and I'm about to bring it all together right now. So we're going to now talk about pressure. Now we define pressure, P, as being force over area. And the area, in our case, is L squared, a side length squared. And the force, we have already decided, is m nu squared over 3L. And we could bring those together, and that would become m nu squared over 3L L squared. And this little piece right here is volume. And so we're going to have m v squared over 3v. Next, I want to introduce a number of molecules. We developed the pressure just as if there were one molecule, and we were talking about the force in all three directions, but now we want to develop a number of molecules. And so we will say that we're going to have n molecules, and that will cause our pressure to be n m v squared over 3v. All right, next I want to go to an explanation of kinetic energy and temperature. We'll start by defining kinetic energy to be proportional to temperature. And then we will say that we also have independently developed an equation for kinetic energy, which is 3/2 mass times velocity squared. Then we can solve for mass times velocity squared and see that that is 2ke over 3. And then we will substitute this little bit into there. And so we will have, I'll put it down here, mass times velocity squared is equal to 2kt over 3. And then we can substitute into here for pressure, and we will say that pressure is equal to N, and we won't put in mass times velocity squared, we'll put instead 2kt over 3, and we still maintain our 3v. And then we'll simply take all of these constants, not the n, but the 2 and the 3 and the 3 and the k, and combine them to be called k, so this will become n kt over v. All right. Finally, we're going to come to a piece. Finally, we're going to come to the next piece, and this is going to be where we want to introduce Avogadro's number. Avogadro's number. Now, we can say P is equal to N, copying from right up here, N times Avogadro's number over itself, so multiplied by 1, times K times T over V. And I want you to note that this little piece, N over NA, is the same as the definition for moles. We'll call that lowercase n. That's moles. And then this other piece, we're going to define Na times K. So we're going to say Na times K is equal to R, and that's just going to be our definition. Where that leaves us then, if we finish this up, is P is equal to, instead of N over Na, I'm going to use lowercase n. Instead of N times K, I'm going to use R. I'm going to keep the T. I'm going to keep the V. And son of a gun, we have found the ideal gas law. I hope you found this informational and that you learned something, and I hope you come back. Thank you.